Swayam Prabha. Digital India. Educated India.
So now we will just go to that this now it is what we call it so we have what you know it's called magnetic moment, and for magnetic moment we went to the called molar magnetic susceptibility, okay, and then you have multiplied by T, so we got called chi-T product, and then the mu equivalent to chi-T product we have calculated, okay. If it is 1.735, okay, it is the one for this is the for one spin and it's for the copper 2 plus and it's magnetic moment in both magneton, and you go to chi-T value it will come into 0.375 for half same value, okay, only different units, but this is the value, this is a centimeter cube Kelvin per mole, okay. And we have shown that and this is the one what is the problem here. So the spins are here and then they will interact through the d orbitals here like this, or through the bridges both they will interact and then they start aligning them with respect to each other, okay, and that you can probe in the at a molecular level inputting the sample in the machine, okay, and then you can study their behavior with temperature. Suppose for namesake we say that these molecules both are spins are here up spin like hydrogen molecule and this is down spin like this, okay. So I supposed to when I put in the machine I supposed to get this is a chi-T product, okay, and I should get the very close to the value very close to 0, okay. I supposed to get here like this near 0, okay. Suppose here is the 0 and we get it here, but I don't get that also, and if they are both spins are up my chi-T product should be somewhere here, okay. Suppose this is value equal to 1, okay, and if they are isolated I supposed to get somewhere here, okay. So this is the case for both spin equal to up, here the case where the spins are not talking to each other and they are not talking, they are far, and the case where the spins are up and down, okay, and it should be temperature independent if they are these are the states are perfectly all molecules are in this way, okay, their spins are. So I take Avogadro number molecule and I measure and I can imagine 3 such cases where one case spins are completely one is up and down, another case both the spins are up, another case spins are not talking, okay. Now when I do that, so now if you experimentally try to see that it comes somewhere like this, okay. Here supposed to be the case for the isolated one, it starts with a little bit less and goes like this, okay. So this is the curve. So now this is 1 point and 5 degree another point, another 5 degree like point. So you have measured, you can measure every 1 point or 5 degrees whatever differences, and if you just connect them they produce the line. So these are my experimental lines, the circles are my experimental lines and the smooth lines are actually the one which are coming due to the connection, just there for your views, okay. So now you have come to a state where you can see here, okay. So now this is your room temperature, this is 298 Kelvin, convert into centigrade into Kelvin, you have to add 273, right, and this is the one. So when I cool down slowly going towards the 0 where my quantum computers are working, and you see that, and here somewhere actually 0, okay, and here maybe 2 Kelvin. Our machine can go to 2 Kelvin, so I put it here 2 Kelvin. So now you suppose this is a 125 Kelvin. So at 125 Kelvin you go there, all molecules are actually arranged in this state. One is up spin, another is down spin. So below this temperature here to here whatever you do, all molecules are in this state. So it is a function, this is a function of temperature, it's magnetic property. So we call it temperature dependent magnetic susceptibility. Okay, now if you are somewhere here, okay, here where value is half of this one, so this is the total value, it's nearly half, and that means 50% molecules are nearly in this randomized state and 50% molecules are actually in the diametric state. So it is a kind of now Boltzmann function. So now Boltzmann, you know, right, Boltzmann. So what does he say? He said that if you have energy states and these energy states are function of something, and then if you cool down or raise the temperature, and you can do the population of depopulation of the states. Okay, so those are the microstates. Now if you population and depopulation if you do, and it has something to do that those states have something to do with physical property, you will see that change, right? So then he said that have the difference in their energy difference between those states, so population will be accordingly vary, and then accordingly you will get the its effect in the property. If it is values are very small, differences are more small, you will get nearly the temperature effect will not work. You know, in NMR machine we apply very high magnetic field. Why? Because to create a tiny amount of population difference between the spin up of the nuclear spin and down nuclear spin, up nuclear spin, those states. And they say that if you take 1000 of such nuclei and you are making only difference in one, you could have made two, actually the signal intensity could have been just double, could have been life have been better. So because the energy difference is very, very tiny, and they are using called radio wave in the magnetic that our NMR machine. When you go to EPR measurement, similar principle, but energy difference is a little higher, and there you just need microwave. The microwave you are putting in your machine, your food, burger, and all, ting, and tum sound comes, it hits up your things. It's a microwave, so it's much more energetic than the radio wave. So radio you put ting ting ting, somebody will come, Raja, and he'll sing something, okay, and listen, okay, and like that. So now here I am now giving the energy, these are all heat energy, and this heat you are feel the heat, and these heat are actually coming as in a like a photon, and they are also having the spin. The each photon has spin 1, don't think they are diametric, they have also spin, okay. And then these spins are actually they are also electromagnetic, and electrons are also kind of, they are electron, right, the electric. When they move they create magnetic field, so we get their magnetic momentum because they are moving, okay. So now you can now imagine that two electrons are in a distance of around 2.8 angstrom or 2.7 angstrom, and they are interacting, and then their properties are changing, they are effective, you can measure, okay. Now what is coming here? So now I suppose to get a case where the two spins are interacting, not interacting, and they are nothing doing, so I get an energy states here, and then I get energy states which is they are interacting, one spin is up, another is down, and third one I have a state which one is like this, okay. So how much will be the separation is actually indicated by this the strength of the coupling. So now I bring a concept where this can further fall, okay. So I can concept, okay, I take no I don't like only capacitate, I keep changing the varying the group here, okay, and they can do something in their the effect. So I put it here R group, and R I can vary, suppose, okay. So R I can vary, okay, let's make formic acid, not acetic acid, then acetic acid, then you get it CF3 group, then other R group which is like CH2, and then C something is going on, I can keep changing. So if I keep changing, what will happen, they will do something in this electron density, they can come little bit closer or can go further, or here be bulkiness, they can distort or something can happen. So I can change near this one, and I will see that, okay, now its effect also will come in this property. So one, suppose another one starts with like this one, okay, Suppose another one comes here. So the orange line I have drawn for the molecule, suppose for the CF3, and here suppose the chi-tip is falling faster. Suppose at instead of 125, it is at 200 Kelvin, it is diametric. What does it mean? That I am changing strength of their coupling called J. So this is called coupling constant, and I am making them more antiphonic than I started with. So then this will fall faster. If I go to suppose this one is going above this one, I am making the strength weaker. So they will not try to fall fast, they will take more temperature cooling to go to the same state. Fine. So you got consider clear. So something called J here. Okay. So J is the coupling constant, and if it is negative value, we call it antiferrometric coupling, and if J is positive, we call it ferrometric coupling. So I can take different anions also, I can couple, and instead of antiferrometrically they can be ferrometric. I will take a case also. Now, so when you are cooling down, so at room temperature, some of the molecules fraction of this. So now it is dealing with 3 states, and every one having some fraction. So this fraction is nearly like very less. This is majorly the case, and some of them will be in this state. And that's when we average out 0 and some of these, and the 0 and some most of these, you get somewhere here. Can you hear me or it's cutting? Yeah. So now this little bit less because some of the fraction are staying in this state and majorly in this state, and it is not occupying here. Okay. If it is occupied, it could have been higher, going upward. So we are making a kind of Boltzmann distribution, and based on the separation, so I can have small amount of this, small amount of this, and majorly this. These are the 3 states distribution, and suppose this is going to be 90% here, this is 5% here, and 5% here. Okay, total 100%. Now if you keep cooling that, this will be slowly gone all, and it will be only these two, and then over the time, and it will become 85, 10, 90, 10, then suppose 90, 85, 15. Okay, like that, it will slowly reducing, and more number of fractions will be occupying this state. So when you have come to this temperature for this acetate ion, and then 125, this is completely gone, all are occupying this state, and you get the diametric state. So if you take the NMR at 125 Kelvin or 100 Kelvin, it will give clean NMR. Okay, it will not be broad and all. If you take at room temperature, it will give broadening of NMR because of the spin center of the copper. So at 100 degree or below 125, it will become like a diametric. At this, it doesn't have any unpaired electron because they completely paired up like hydrogen gas. Okay, and if you come again on the sample, they will start coming to the occupying this as the energy states. The same molecule, only say slightly like things will be different, same molecule only, but they will be again those states will be occupied. So it's a reversible. It's not irreversible. Once you cool it, you reach, and you can cool warm it up, it will come back to the similar state. So it's a function at what temperature you are keeping, it depends on the temperature. Okay. So now how to measure this one also? I put another curve called chi-t versus t m versus h plot. Okay. So this is to call it is antiferrometric coupling, and another temperature called ferrometric coupling, this one, and then if you measure it, measure is m versus h. So now same sample, now what we have done, we have applied a bit of magnetic field, and then we have cooled, the field is kept same. Here field is kept, suppose H equal to 0.1 Tesla, 1 Tesla equal to 10,000 Gauss, and it is fixed, temperature we have varied. Now what you have to do here, field will change, temperature will be fixed. So you can suppose go to 2 Kelvin, okay, and then you measure this 10 Kelvin, 100 Kelvin, you have to fix it, machine will fix the temperature, give the sample the temperature, and they will change the now field, it is the reverse. Now it will go to our machine can go here 1 to 9 Tesla in IIT Madras, okay, quite high. Now it will be coming, how the it will come. So if it is at 2 Kelvin, here you have seen it is a diamagnetic state, so it will be coming like this, okay. Because at it is diamagnetic, at its low temperature is diamagnetic, it will not give magnetization, okay. Now I take once another case, so where ions will be differently oriented. So suppose I make a molecule and I change them, this molecule here I put instead of a 2 acetate, I make mixture of acetate and azide bridge. So azide you know, right, this 3 nitrogen anion, it's called azide, this is minus. And then if you couple with this one, okay, so my charge is balanced again, but I have just make a mixture of compound where this is not 2 times, okay, this is 1 time, and I have actually so that was 4 times, now it is 2, and azide has come now 2, okay, and again same water molecule. So now what will happen? So instead of such kind of bridging, so here and then they will be like little bit maybe elongated or something can happen, some changes will be in the distance and structural aspect, okay. But now same 2 copper ions, so same spin center, now they are coupling through different bridge, okay. Now this depending upon the angle, it could be ferromagnetic and antiferromagnetic. We have they have measured different sample and they have found. So what they found, if she is this angle is near 90 degree, they will give you this state, 2 spins are up. If they are going above crossing in 109 like above 90 degree going to 100, 125 or 110 something, they will favoring this state, okay. So that is the coupling they will bring. Now here the coupling was with the through the this many atoms, here is coupling through these ions. So have you heard of the name called super exchange, double exchange? No, okay. So now the concept all this coupling, now I introduce a concept called super exchange and double exchange, okay. Now if you have a spin here and you have a spin here and you have a diamagnetic ion, suppose oxygen or acetate or nitrogen, whatever, sulfur, anything, and they are connecting the ions and they have filled p orbitals, okay, and these p orbitals they are having the spin, okay, up and down, and this spin with respect to couple with the opposite spin, and okay, up this is down, and then this spin down it will couple with this one, overall they will mediate, put them like this. So the 2 electrons which is in the p orbitals paired up, okay, non-bonded one, non-bonded the non-bonded electrons, they will be coupling 2 spins, suppose here, okay, in this state, opposite fashion in this way. So the up spin here will make this is down, and this is down spin here, make it keep it up, overall this is down, this is up. So overall it is a case situation which is this is called antiferromagnetic ordering, and this is called super exchange, and this exchange depending upon the angle. If you twist the angle, okay, and this situation can change, the spins could be upward or this spin could be remain downward, okay. So this we can do by, I am just keeping either of this option, so either this or this, okay. So that you can be depending upon this angle. Sometimes for some ions it depends upon the distance, for iron it depends on distance, for copper or nickel then they depends upon the actually for isotopic ions they depend on the this what do you call it, super exchange and this angle, okay. So if it is 90 degree angle, near 90 degree, it's not going in far, it will be ferromagnetic. If you go beyond, going less also problem, going far also problem, they make them antiferromagnetic, okay, fine. So now if I get a case now which is similar and only curve signature will slide up or down, but it will remain like that for antiferromagnetic case. Now I make some compound where this angle is near 90 degree and it is strongly mediating coupling. So my spins will be, instead of going downward, it will start little above and it will go like this. Okay. Now where it will reach, that also I can predict. It will reach, you have the, for 2 spin you have seen, if you calculate, we have got value equal to 1.01, right. So it will be, if it is strongly coupling, it will reach to 1.01, it will becomes constant. So it can maximum reach there. Okay. If G is 2, if G is more, it will go little more. Okay, because the formula you have G. So D is constant, the S used to be, if you keep S constant, it will reach the maximum value. So now when it was randomized and you have calculated, when it was 0, you have come to 0 value. Now if you put S equal to 1, so after coupling it will reach to 2 spin equal to 1, and then value will be coming here nearly 1. So this value will be coming near 1 and maximum, that more than that it cannot reach if G is 2. If G is more than 2, it can be, and G depends upon the ligand also, okay, and the structural distortion and all. Now if you now measure the same thing, so here the case was dropping, here what will happen? So in that case this difference is happening, then is reverse way arranging. So now because of favorable coupling, on cooling, this is the ground state and this becomes the, it will just reverse. By coupling you are making the ferromagnetic states is more stable and then the antiferromagnetic state. So when you cool it, so it will occupy the ferromagnetic state instead of antiferromagnetic, is just reverse, and then curvature will change. Similar way I can put dot lines here, bullet point lines, circles, and my data points will come like this, and then the temperature where it will become fixed, it will not go, it will be. So this is a temperature where I have come to a temperature, my molecule all are in this state and they are ferromagnetic. So if I measure the magnetic now property, now this one, same one, it will come 2 spin. So 2 spin equal to the call, or magnetization called MS value G into S. So G is equal to 2 and S equal to 1, half plus half equal to 1, plus half equal to 1. So if you put it, it will come near 2 mu beta. 1 mu beta is for 1 electron, 2 mu beta for 2 electrons, okay. So it will be coming here, it is a 0, here 1, here 2, so my values will be coming somewhere. So if you extrapolate this one, it is near 2. So this value, what is the value, that many unpaired electron will be there. So for 1 electron it will be coming here, for 2 electrons it will be coming here. So if you measure, it will give you, this magnetization plot will give you, for the case where it is ferromagnetic coupling, this is the case. Okay. So if you are asked copper acetate is diamagnetic or paramagnetic, you have to say it is paramagnetic at room temperature. What does it mean room temperature? You said, sir, if I cool it, it will change. So if why it will change, the class I explained, you can say. At what temperature is diamagnetic? Suppose below there is a temperature, literature value, you have to see exact temperature, I may not have written. Below somewhere around 100 Kelvin or something, it is diamagnetic. So below that temperature range, every left side close to 0, it is always diamagnetic. If you bring somewhere the above 100 degree, somewhere depending on what temperature you are standing, some amount of this state, randomized state, and some amount will be antiferromagnetic state. Okay. So more close to 100 Kelvin, more diamagnetic state, more close to room temperature, more is close to the randomized state. Randomized means spins are like fluctuating through this thermal heat. Okay. And what is the thermal heat? T and its multiplication with the kV. So if I am 100, I am sitting at room temperature, its thermal energy is getting Boltzmann's constant multiplied by 300. If I am the same one sitting at 77 Kelvin, that means liquid nitrogen temperature, 77 Kelvin multiplied by Boltzmann's constant, that is an energy. Now if I go to 0 Kelvin, close to 2 Kelvin, 2 multiplied by the same constant, that means keeping the sample here and keeping the sample here are difference by 150 times. So you are giving them energy difference 150 times. So, and that's the effect you see in them. Now, if the molecules, you get some molecules where the spins are not interacting at all, what will happen? They will remain here fixed like this. And a low temperature slightly decrease because of the slight antiferromagnetic interaction between the molecules. Otherwise, they remain like this. So, this is called paramagnetic state. This is a antiferromagnetic coupling state. This is ferromagnetic coupling state. You don't call it antiferromagnet, don't call it ferromagnet. These are the type of coupling. We call ferromagnet, antiferromagnet when they have ordering. Okay. Now we can go a little bit of those now. Okay. So now at least you know one molecule you have studied in your textbook, its detailed property, and this is a key concept I taught, and it's so general. So instead of keeping 2 copper ions, you can put 2 organic radicals, they can couple. Okay, so the since will same thing. Now instead of putting 2 copper ions, you put 2 nickel ions. Only S will be different, but situation is same. Now instead of 2 nickel, 2 manganese, 2 gadolinium, their spins are higher, but situation will be same. Now I take a case where 2 gadolinium I can take. Okay, suppose I take 2 gadolinium, so GD 3 plus and GD 3 plus, and suppose they are coupling through one oxygen, so suppose through a bridge, and they are coupling. So what will happen? So S equal to first one, S1 will be 7 by 2, it has 700 electron, other one is having 700 electron. So how many states it will produce? It will produce, states will be 7 by 2 plus 7 by 2, this to 7 by 2 minus 7 by 2. What does it mean? Means that both the ions having each one having 7 ions spin, this 7 spin can all could be together upward, and one could be upward and the could be downward. And then what are the states possible? So now here we will start this equal to 0, then every time difference by 1. So 1, 2, 3, so this you sum up, it will be 7, 4, 5, 6, 7. So these are the spin state possible. Okay, and again the Boltzmann distribution come like this. So when you cool the sample, instead of going between these 3, they will go between these 7 states. Okay, and then the Boltzmann distribution again will start. Now it depends upon the coupling ferro or antiferro, and it will be behaving this way or that way. Instead of having this value, its value will be put is 7 by 2. If you put it, it will be a lot. It will be around, what is the 7 by 2 if you put, what will be coming? I think I have a book here. Okay, so there is a table. I can share you this book PDF also. So 7 by 2 spin will be 7.87. Okay, 7.87 KT value. Okay, for 1 gadolinium. So now if you have 2 gadolinium, so you can multiply, it will come around 15 point something, right? So 15 point suppose 6. Okay, so instead of this value, it will come 15.6. Nature of the curve could be similar depending on J, but the values will be, the philosophy is same. So I will get a curve suppose here whose value will start 15.6 or something, and then if it is antiferromagnetic coupling, it will come like this. If ferromagnetic coupling, it will go like this. Okay, and what is the things? Now it will go in this one. If it is antiferromagnetic coupling, so it will go from randomized state towards more slowly towards this, and if it is ferromagnetic case, from randomized case 2 was go towards a 7. Okay, so if you ferromagnetic case, they will all slowly turn upward, and they will try to go to the high spin state. If it is antiferromagnetic couple, they will go try to populate towards this state, and that's why you see in this nature. So KT measurement tells you the nature of the electronic coupling and the electronic state, and they give you some amount of stability, and that's the thing we calculate and try to study. It's a characterization of a material. Okay, because they are mostly NMR, they are not so good, they will be broad and all, and magnetization, EPR, those are the one which will be suitable. Okay, done. So now if instead of having gadolinium, if you have manganese 2 plus, it has 5 unpaired electron each, and similar case if I take manganese 2 plus and coupling, so I have to forget till here, so they will come 0 to 5 states. So if I keep nickel, 2 of the nickel ions, if I take, you have to forget this, and they will be starting 0, 1, 2. So This is so general. So, population depopulation will happen, and this number of state depends upon how many electrons they are coupling. Okay. Now say we have done homo, what about hetero? Suppose I take gadolinium coupling with the manganese 2 plus. Okay. So how it will happen? 7 by 2 minus 5 by 2, it will go 7 by 2 to plus 7, 5 by 2. That's all. So here again 0, here it will come, this is 2, how much it will come? 2 by 2, okay, so 1. So their state will come between these two states. If I have a, instead of manganese, if I have a copper ions, okay, so copper ions if I put, so it will have half, so half if you add, oh sorry, I have done a mistake here, it was 5 by 2 means it was 1, and if you do this one, 5 by 2, what was coming? 12, that means 6, okay. So now if you have a copper 2 plus, so it will, instead of having this, so it will have a 3 by 3, and this will be 4, right. So 7 plus 1, 8 by 2, 4, and 7 minus 1, 6 by 2 is 3. So this will be the states only. For copper, this couple, it will have only 2 states. For manganese, you have many more states. Okay. So depends upon, so it is general procedure, and how many states will be procedure. It will be S1 minus S2 to S1 plus S2, and every state will be defined by 1. So here 2 states are only possible because difference only 1. In the other case, we have more because they have difference, we can make more. Okay. So now done. So now I go to a concept called, I use a concept which is called spin coupling, and I will introduce a little bit something on it, and it will become something very much useful in the molecular magnetism. Okay. So this is the way we are calculating the, what do you call it, calculating the spins, how they couple, and then how they interact. Okay. And the mechanism we have said, this is called super exchange, and this is a ferromagnetic or antiferromagnetic depending upon the angle and sometimes distance. Another concept called double exchange. Okay. So what do you mean double exchange? So double exchange happens, instead of electrons are not jumping from here to here, they try to couple through them, right. Another case happens, the electron can hop between the atoms, and suppose manganese, the famous example is manganese 3 plus and 4 plus, okay, ions. So this is a D4 system, and this is a D3 system, okay. And now you also have this, so if you do that, both are octahedral if I take, and now I have, these are the 2 states, okay, T2G Eg, and here also like this, and here 3 electrons which are like this, okay, and here are the electrons, 4 electrons which are like this, and then bit of electron distortion, it will be here, okay. Now what happens in this case, you are thinking that electron you can only keep in this 3 or like 4, but they are mixed valent. Mixed valent means the same ion but in different oxygen state, and this is called mixed valence because valency number is different. In this time, this electron instead of kept coming here, it goes to here. So this becomes manganese 3 plus, and this becomes manganese 4 plus, and the electron you have kept earlier there, it has come this side. For you, how does it matter if I keep this one here or this one here? Does it matter? You hear a little bit different? Same. So, but little property will become different. So now property is different. When these guys will see, they will see little bit different angle, and when you see, it will be different angle. So when you measure, it has a something. Now for system, it is nothing. It said my chalk was in this hand or in this hand. I am weighing the same, okay, but this leads to a situation where It's like waving my hand. So I am keeping my hand to like this, okay. And I said, okay, how many hands I have? You said 2 hands, sir. Now I say, how many hands I have? Till 2, sir. Then I said, how many hands I have? You know 2, but when you are coming outside and you cannot count, okay. So you know there is one person called Arjuna, not that Arjuna who was fighting in the Mahabharata in the Kurukshetra, another Arjuna who had 1000 hands and he was alone fighting with enemy. So at one point he went to a river and started propelling his hand, and then Lord letting the water to flow down, and he created flood to the other side, and all this the soldiers are dying, okay. So moving hand you can understand what can happen. With 2 hands you may not be able to do it. He with the 1000 hands he could do it. So now situation is the thing that is that when you do this, it leads to a situation which is called double exchange, and this effect comes on that these pins will be coupled always perimetrically. So this case is forget this state and always this state, and its coupling will be very strong, much stronger than the super exchange. And another one, if you bend this angle by 10 degree, it will vanish, it will become super exchange, okay. So double exchange is a property, same ion in different 2 oxygen state, and they can couple and always give ferromatic coupling called double exchange. And if it is, you can tune the angle, it will nature will change to super exchange and will be weaker, and also materials property will change, okay. So they are used in some materials, okay. And okay, so now I taught some concept now, right? Okay, so now I go to a last concept of this lecture, where now you know what is called super exchange, what is called double exchange, and you know what is coupling, how the values coming, and how to compute, like experimentally find, okay. Now the last concept is that from now around 40 80, yeah, 45 years ago, one scientist called Lees, he made a compound and who is called manganese cluster, okay. So he produced a cluster which is like this. He has in the outer ring 8 manganese, okay, 3 plus. Today I took the example little manganese 3 plus. So he had 8 of them, okay. Now did I write 8? Okay. So how to draw 8? 2, 2, 2, 2, 2, 2, 2, always make 2, 2, 2, okay. You don't try to make only 1 and then 2 and then 3 like that, just opposite will do, okay. This is a 1, these are 1 manganese 3 plus, okay, and you know manganese 3 plus has Ian-Taylor's distortion, and you only know Ian-Taylor distortion, but is Ian-Taylor distortion something to the preference of the spin. So when you do a distortion, you are keeping the spin along the z axis. So it has anisotropy along the z axis like this, okay, and this is something to do great to your molecule, okay. In copper you don't have such thing, it has under distortion, but it doesn't keep the spin always along the z axis, okay, but in manganese 3 plus it does, okay. Now you have another kind of ions which are called manganese 4 plus, which is is like a disc like this, other comes like a cube. So if you made a cube like this, and then in cube alternatively here you have manganese, here you have manganese, here you have manganese, here you have manganese, and remaining all are oxides, oxide, and oxide. So he had 4 manganese, so these are the 1 manganese 4 plus, and here she had 1 manganese 3 plus. So this is D3 system, this is D4 system, and it has JT distortion, okay, this one doesn't. So this is isotropic, it's called isotropic, okay, because spin density is everywhere similar or everywhere same, it is more along the z axis, so it is anisotropic, okay. Now these two when they are coupled, now they have some kind of bridges further with this, okay. So always they are coupled. So I have a cube heterometallic cube and oxygen and oxide cube, and I fit it inside a disc, and they are coupled with this one, and then periphery you have the same acids are coming. Okay, how many there will be there? 8 again. Okay, and these are the 8, and what I mean with this one is equal to this, and 2 oxygen is a monoanionic. Okay, is the meaning. And these are the manganese 3 plus, and here the manganese 2 plus. So I have 8 in the periphery and 4 on the top, like this. Something like that, bridging like this fashion. Total 4 up and 4 below. So I have 8 on the periphery and 4 in the bottom and 4 and the top. So total 16 acidates are there. 16 acetate. Okay, OAC groups, and they make this one isolated. So I get a molecule which is actually isolated, and the property will not come because of the interaction with this one with the similar molecule from another one, because they are very far. So their molecule property will only come like copper acetate only from this core. Okay, and this is called, I can define them as a molecular magnet, because property is coming from the not interaction with each other infinite times. It is coming only from this core. So you can call it molecular behavior. Okay. Now when they coupled, now situations are the same. Okay. Now when they are coupling, the coupling becomes, now I can, so they found this molecule coupling had a 2 kinds of ion. So you take 3/2 spin for the these ions, right? 4 by I use this code, pencil fine. So you have 8 of, how many of them are? You have 4 of them and 8 of them. Okay. So 4 multiplied by 3/2, this 3/2. Okay. D3. Okay. And now you have 8 multiplied by 4/2. Okay. So if you do this one, how many you are getting? What is the value? 16. Here you are getting 6. So now my calculation starts. So this core can behave, can coupled with this core either upward or downward, either ferromagneticaly, anti-ferromagneticaally. So now if I make a case where these spins are going to now couple, I am producing 16 minus 6, 16 plus 6. So I produce here 10 and here 20. So these are S value. Okay. So I can produce, these are the possible spin state. Sorry, this is 22. Okay. Now 22, these are the states. So now what they have found, this molecule experimentally, that it is the case, this one. Okay. This is the case. So where all the spin, we forget about the periphery, only this core, all the manganese 4 plus ions, they are coupling with each other within this core ferromagneticaly. Okay. So that means you have a cubane, these are the 2 top like this, and this also 2 all like this. Okay. They are producing this. Now the other one they have, they are all ring, they are having in this way. So these are all upward, suppose. Okay, now I put them downward little. Okay, so downward, all of them, and these are the one which are also coupling among themselves opposite to this. So they will be all upward. I am putting little bit longer value because of their, they have 4 ions, so 4 spin, and they have 3 spin. Okay, so if you do that, so I get a disk which is, this inner core is actually having the spin equal to 6, outer core is spin equal to 16, but overall when they couple their vector, they give me the state of the equal to 10. Okay, and this is the one which is become the first molecular magnet, which was characterized 10 years later by another group, which are promising material, a class of material called single molecule magnet. So instead of storing data in domain where you need billions or trillions of ions, you can store every in 12 ions the same amount of information. Okay. So here what happened now, it does, So my S equal to 10 is called well defined spin state, and its chi t becomes like this. So it goes little bit down and it becomes 5 6 like this. Okay, and here is the one which is corresponding to S equal to 10, and magnetization becomes like this, nearly it is 20. So you have 10 unpaired electron, its value will be around 20. Okay, this is M versus H, this is chi t versus T, and you see this is a kind of ferromantic coupling and little bit antiferromantic coupling also there because of themselves. Okay, so now what's big deal about it? It has a big deal. Okay, the deal is that this molecule moment you put in a field and then they have enter distortion, and enter distortion will bring zero field splitting parameter, and which is negative, and which is actually going to change the thing. So it produces two whales. Okay, so you have seen Zeeman splitting, right? Zeeman, if you put Zeeman effect, spin will split, S will split into MS, right? So if you have S equal to half, it will become minus half plus half. S equal to 0, 1, minus 1, 0. So now minus like 2, minus 2, minus 1, 0. So now you can imagine S equal to 10, what will happen now? So minus 10 all the way to plus 10, right? Including 0, right? Yes, that is a significance. Now if you do that, here is the 0, okay? This is the MS, 0. Now here will be minus 10, minus 9, like that, minus 8, all the way it will become minus 1, and this side will become plus 10, then minus plus 9, plus 8, by the way here will be plus 1, right? So and all the states are here. So this is called double well, and here d equal to negative. It becomes d equal to positive. In this case it is not actually experimentally found. It is similar curve, it will come, but it will look like this, where here is the S equal to 0, M is equal to 0, and here will be the minus 10, here plus 10, and all the way. Here d is equal to positive. Okay. But in this molecule, this is the one case found. Now it has, when the molecule you apply magnetic field, it is all spins are here and they are not here, and then it has to go, it cannot go here to here, so spin has to climb through here and only go there. So in this way you can trap the spin and keep in one of the well. So now you see I was keeping my data either this state or this state, okay, up and down in the domain, and where I need lot of molecules, I can now a lot of ions I can now do in only this one, a small molecule, and which will do the same job. I can keep either in this well or in this well. If I don't want them to go to other one, I only have to increase this well height, that's all, and where I can store the data and I can keep it. And then this molecule can give you at 2 Kelvin, if you want to use this, you can store 10,000 times the data you are storing. Okay. So now got it. So this is a condition where the D means the zero field splitting, and the zero field splitting is coming from the spin orbit coupling, and this is because of the enter distortion of the manganese. So spins comes and manganese 3 periphery ions, their anisotropy comes perpendicular to the disk, and that the spin and the D together gives this energy well in this way, and then you can keep. In this case you cannot do, because always the heat will fall to 0 when D is positive. When D is negative, you keep the 0 here, and these are the two possible state, and then they have to go there. There is a possibility also can go here to here directly, that is called quantum tunneling. Okay, so quantum tunneling actually reducing the energy barrier, not good for us. So then they applied magnetic field a bit to magnetically slightly they will make non-degenerate, and they cannot do that. Okay, that is called suppression of the quantum tunneling or magnetization. Okay, so you can control it by the field and all, and you can create such thing, and you can use it for your next generation of materials, molecule based electronics. Okay, I am sure one day you will use a material which will have some kind of metal ion and not nanoparticle anymore, where it is stored and much more data. So nowadays the molecule, you have no ferrocenium ion, right? Ferrocenium ion. So its corresponding dysprosium cation is a lanthanide, one of them, and with the ferrocenium like this, vein structure, it is storing the data at 80 Kelvin. So for nearly 30 years, 35 years, it was nearly below 10 Kelvin. Now this similar property was found. Instead of S here, they have actually J labels. This J labels. J means Russell-Sandler coupling. L and S coupling. You know that L and S. Term symbol you have studied, right? When you have spin orbit coupling, L and S will couple. Okay, there, and it has minus 5 by 15 by 2 to plus 15 by 2. Similar OL, but this side minus 15 by 2 to all the way to minus half. This side plus 15 by 2 plus half. So like this OL will be there, and they are storing the data. And finally, in this one, you can, it is made in maybe 5-7 years ago at that temperature, highest. Okay. So I am closing my talk here. Okay. So you will get the there now thousands of papers are there in this field, and the part you have studied in inorganic chemistry. Today I taught a bit of magnetization, some of the bit of concept. I only use 4 formulas. I don't want to scare you, and I have only used diagrams and only key concept and nothing to memorize. If you look at these diagrams and the concept I taught, and look at the videos, few times you watch, you can really gain very clean idea. And in laboratory you play with the chemicals, you can make molecules, and then you can study their property, you can explain. Okay, and then you have to keep playing with the recipes, make different molecules, the properties you have to, parameters you will get, coupling constant may be difference, organization difference, this is different, that is difference, but finally something is same, concepts are same. Okay, so you have any question? This is completely new for you people, not a single thing you are knowing. Okay, good. But these are the inorganic chemistry concept. Okay, so now you can just bring it to the, this will connect MSc to PhD. So there are a lot of people in India and foreign, they are working on this topic. People also can do PhD in this kind of topic. Okay, so I see you.
SwayamPrabha, Digital India, Educated India.